Okay, so this is Tmua 2022, paper 2, question 19. Now, this is an interesting little question because what they're saying here sounds like it makes sense because whenever we think of a regular polygon, that describes it perfectly. So, what we're really trying to do is sort of break this rule. Now, if we think about why a polygon wouldn't be satisfied, sorry, would be satisfy all of these but wouldn't be regular. Well, it's probably worth thinking about just drawing a single sector in and saying, right, how can we have two triangles with different angles but the same area? So I'm going to draw one now that doesn't have, they clearly have different areas. So we want this theta and this alpha. And then we want the area of, say, this A1 and this A2 to be the same, but for different values of theta and alpha. Because that's what's going to make it regular if all of these angles are the same. So we're going to try and break that. Well, if that were true, if A1 would equal A2, that would mean, remember, all of these sides of triangles are isosceles. They've all got side length r for the equal sides. And so A1 would be half r squared sine theta, and this would be half r squared sine alpha. Now, clearly, we can divide both sides by half r squared. So what we've got here is that A1 equals A2 if sine theta equals sine alpha. Now, if we think about why sine theta will be equal to sine alpha, one obvious way is if alpha equals theta, but we're trying to find one where that's not true. Let's just think about our sine graph. So here's our x, we've got sine x. Now, if sine theta equals sine alpha, and of course, we've got this, we've got two values. Now, those two values will always add up to 180. So, if they're equal, that either means theta equals alpha or theta plus alpha equals 180. So now I'm thinking, well, can I make polygons where I've got all of these properties satisfied? However, at least one of the triangles has got an alpha and the other one's got a theta, where the two add up to 180, but they're not equal. So let's see what we can do with that. Well, if we have our circle, let's imagine we've got loads of little triangles that are all the same. All we need is one triangle to be different. Now, if we want, say, because we need the two angles to add up to 180, we're going to have a straight line. So if this is theta, and that's alpha, this is theta, then those triangles, these two here, are always going to be the same. I'm just going to, I've got some dodgy drawing here, but it's that one there, and let me try and color this one in green. This one here. As long as this is a straight line through the center, then these two triangles will have the same area. And then all I have to do is all this, the rest of the rest of this can just be all the same. So these are all alpha. Okay? So it seems that I can make an irregular polygon that satisfies these three conditions as long as I can make two angles that add up to 180. So why would I not be able to make it? Because at the moment I've gone from thinking, well, all values of n to no values of n. But maybe I can do it for 3. I definitely wouldn't be able to do it for 4 because you can see here if I just had like a rectangle like this. Here's my center. I can do that. There's alpha, there's theta. They add up to 180. So this area 1 would be equal to area 2. That is not regular. So I wonder if it's 3. So it's definitely not that. It's definitely not 5 and above. It's definitely not all. So it's either none or 3. Now, if n equals 3, that means a triangle. Now, can we make a triangle if we've if we do this? So we've got to have a straight line going through the center, and then we've just got to have one other point. So we'd have something like that's our triangle. But the problem is, of course, now the center of the circle is not inside the polygon. So for the center of the circle to be inside the polygon with the triangle, you've got to have a vertex here. This one cannot go through the center. And then this can't go through the center. So yeah, it will work for a triangle. So the answer is B, 3 only. So quite a sneaky little question, but definitely drawing us into trigonometry when we look at trying to see why the triangles would be have different angles but the same area.